Okay. So just to quickly review over this exercise that we did last time. We started the lesson on numerical methods for differential equations. To be precise, ordinary differential equations that are initial value problems. That means that we're starting from a point, let's say this point, and we're gonna from then on iterate. Let me put it in the presentation mode. We then iterate after that. We start from this point and we approximate the slope to the function at this point and basically extrapolate to a predicted value using that linear function or the slope. And that's essentially what this equation is. Since my slope, dy dx, is actually f of xy according to the equation, I simply substitute when I'm doing this step, I simply substitute here f of xi yi as dy dx at point xi. And that gives me a value y at this next point in my discretization. Cool. So we actually did an example, and naturally with the reduced step h, I will make less error. Okay. So my solution will improve as I go down. Did everybody get to program this or finish it up? You possibly don't remember what happened on Friday? Okay, so I'm just gonna quickly look at it in the code. And I don't think that I finished it while doing it in front of you. Okay. So this is my Euler.m. It's actually a script. I wrote it as a script last time while we were here. So this being a script, I gave it h and x. H rather. So what I'm going to do now, and we had this one was my y1. So I'm going to now turn this into a function that I can call multiple times. Okay. So let me quickly do that. I'm going to say save as Euler method. And I'm going to say function x, y is Euler method. And my input is h. So the moment I put h as an input, I'm going to comment the one that I had in the script so it doesn't overwrite the value that I passed to the function. What else do I need? I need x1 and y1, right? And y1 is this. And I also need my xn as an endpoint. So that's my interval. And then this is what my x is going to become. Yes, based on the input of the function. And that should do it. So I also need to end the function up here. Okay, save. So now the way I'm going to run this is as follows. I'm going to run it with the values chosen. 5, this was 0, 1, and 4. There we go. I'm going to actually now turn off the plot inside the function. And I'm actually create a script that is going to compare solutions for this using different h, right? So that's why I needed a function so I can execute it. So I'm gonna save this as a script or example Euler method. So we're gonna do this. So that's my first value. I think I need to do it 3 times. This is wrong. Point 0.5, 0.1, and 0.05. All right. 0.1, 0.05. And then this is gonna be some new, I'm gonna say x1, y1, x2, y2. Okay. And now I'm gonna plot them all. Plot xy and xy I'm gonna give in blue and put stars. Plot x1, y1, red diamonds, and let there be a line as well. What's missing here? Hold on. So that it doesn't overwrite the plot, right? So that way, all of them will be plot on one plot, and then plot x2, y2. What other? Magenta. Okay. Magenta, symbol, square. And I'm missing analytical. So XA is gonna yeah, x2 is fine enough. And then I'm gonna say analytical solution is here. So y analytical minus 0.15 times XA, no, 4, plus 4 times XA, 3 minus 10 times X2, and okay, XA. All right. Hopefully I did that right. I'm gonna see the moment I plot. So just a line, no symbols. All right. Ready for a moment of truth? Oh, we need the legend too. H is 0.5, H is 0.1, H is 0.05, and analytical. Ready? There we go. Ah, of course. GCA font. Oops. Here we go. Questions? Everybody's too sleepy for questions. Okay. So basically, as h improves, so does my solution. Well, we can still do better. Okay. And we're going to keep improving on this, as a matter of fact. So Euler method altogether is still just a first order method. So that doesn't mean it's very accurate. Second order is desirable if possible. And there are now various ways to improve on that. There's next one is so-called Hoynes, which says, and I'm pronouncing this in a weird German way. I did learn some German, so I say Euler and Hoyne. Bear with me. So I'm not even certain what would be the English version of these two. Maybe somebody could help me out. But basically here, instead of going to our next slope, one thing that we can do to improve is say, okay, this would be the slope, the original slope that I'm taking to get to this next location. Well, I can actually pre-compute what the location, well, I know what the location is, xi plus 1, and I can pre-compute this yi plus 1, and I can figure out what is the slope there. Okay? And then instead of taking this as my final value for y, I'm going to update it, and I'm going to average the two. And in this particular case, it obviously does a slightly better job. Okay? So this was too steep. This is a little less steep. The average is less steep. So I'm going to get here, and I'm going to get more accurate. So it's actually really easy to, this is another way to look at it. So this is my original slope, okay, just on a slightly different case. And this is my new slope that is from here, so it's parallel to this black line. And when I average the two, I get this slope, which is better accuracy. Okay, well, we can actually really, really quickly adapt Euler method's code to Hoyne's method. Let's try to do that right here. Save as Hoyne method. Change the name. So what does it say? First, treat this value that we used for Euler method, treat it as a so-called predictor. Okay? So I'm going to say predictor value. I'm going to call this predictor. I'm going to call it y0 right now. And now, instead of what used to be this, So my y of I is this previous value, and it's this slope that is changing. So I'm going to actually now take that as a separate. I'm just going to say slope is f of xi yi minus 1 plus f of x of I and this predictor value y0. So that's my slope at the new point. And I want to average the two. So I'm just going to take 0.5 times their sum. And that's my new slope that I'm using. So instead of just this, which is what we had in Euler's method, I use that. I use that to find my predictor value y0. So basically, I'm getting this point here, this point here. Let me go to the old plot. So I'm getting this point, right? And then I know what y0 is the y value for this point. So I will evaluate slope at that point, which is f of my next x and y0, okay? So this is my previous slope. This is this new slope at the new point times 0.5. So let's compare the two. Maybe it's good. And I can do this actually multiple times. I can actually keep repeating this little loop here, but I'm just going to do it once. Okay. So I'm going to, in my next exercise, I'm going to say x3, y3 is that new function point method of the same. I'm going to compare it with the first one. And I'm going to do a new figure. I'm going to plot my xy, which was Euler. I'm going to say hold on and plot x3, y3. I'm going to give it some symbols. What are the colors? Blue, red, magenta, green. Green stars. I'm going to do both stars. Blue stars. I'm just going to execute this part. Oh, and of course, so I'm going to compare Euler and Hoyne. So this is the whole point of reusing the code. Most of the code that I have figured out for Euler's method remain the same. I just basically adapt this portion here on how I'm stepping. Okay. I didn't plot analytical solution, I should have, but I can see that this Hoyne is definitely closer to the analytical solution. Yes? Let me correct that quickly. There we go. Good old cut, copy, paste. And I'm going to use red color because green is really bad on the screen. There we go. So it is better. I can improve the method. Let's now take this on steroids. Ready? So first improvement that I said, you could actually iterate this corrector equation. So you'd either say, hey, do this 5 times until you improve, or you could also say, do it until error is small enough as usual. So set some epsilon and get better. We're not going to go there, but that's a possibility. So this is basically how you kind of loop inside. At each step, you just keep doing this correction until some error between the two values is small. Okay? So this is what we just did with Hoyne's method. Now let's actually take this on steroids. Okay? This is going to be very, very, very accurate method, and you will see how even with h is 0.5, which is pretty large step, I'm going to be right on the money. And the way it's done is that basically there's this slope. Okay? So just a moment ago, I put the slope as the average of 2 values. Now I'm going to actually take 4 values and get sort of a weighted sum of all of those 4 values. So I'm going to figure out 4 different slopes, and I'm going to weight them in such a way that I'm going to get really accurate. And it's not, nobody pulled out those slopes from thin air, okay? They were actually pulled out from Taylor series, okay? So they were adjusted in Taylor series so that all of the terms, the initial terms that you have, kind of cancel out, okay? Up to the 4th one. Okay, so that's kind of really pushing it. So let's see geometrically how it's done. These are the 4 slopes. Okay, so technically you take the first slope as this Euler's method slope that we had. Okay, and then on next one you estimate slope at a half point in between. So you take this slope sort of halfway, and this is your new y, and at that y you estimate the slope using the function f. Then you take that slope also halfway, and you get the 3rd slope. And then you take this 3rd slope all the way by step h, and you estimate what the slope is there. So this is literally your 4 slopes. Here's the geometrically how it's done. So basically at this point, I find my slope k1, that's actually this one. Okay. Instead of taking it all the way by step h, which is what Euler method does, I'm going to just stop halfway and find what my estimated value y is. Okay? At that estimated value, my function f for that x and that y has certain slope. That's this slope, k2. Cool. Now I'm going to get that slope and again start from this point and take it halfway. Find my estimated y. Okay. For that y, again, I have certain, for that y and that x, again, I have a certain slope k3. Okay. Awesome. So I'm going to take that slope, k3, and I'm going to extrapolate from this point all the way, entire length of step h, and find my final slope at that point, which is this one. And then the slope that I'm actually going to take as to get me to my next estimate is a weighted sum. 1/6 of k1, 2/6 of k2, 2/6 of k3, and 1/6 of k4. 1/6 plus 2/6 plus 2/6 plus 1/6 is 1. So whenever I have a weighted sum, all of the weights should sum up to 1. Okay? Yeah? That's it. So it's quite a bit to write down, right? But it gets really accurate. So guess what we're doing right now? Let's try that out. and you want to work from your, well, from Coin's method. Essentially, you save it as this method, again, German name Rungekuta. You will also hear Rangekara, which is the English way to say it. So these are your formulas for K1, K2, K3, K4. I'm gonna let you, or rather, I'm gonna disconnect. Or do you need this slide? Okay, I'm gonna leave it then. I'm gonna stop the video so there's no like silence.